Hello, these are the problems for chapter 14, angular momentum. Um, like I said in the theory, at my university, the dynamics course, we didn't really go over angular momentum like that detailed. So the questions are also not going to be that detailed. On our final exam, it was just one multiple choice about it. So apologies if you needed more stuff about angular momentum. This is all I got. So I got three multiple choice questions, and I got this one written that I found. So I'll just go over those and walk through the process of how to answer these multiple choice questions. So, anyways, block two. So for question one, block two has three times the mass of block one, and they are arranged as shown in the figure. The figure is this here. I wrote the info ahead of time just to not do that. So, anyways, the rope is massless, but the mass of the pulley is not negligible. After the blocks are released from rest, which of the following best describes the direction of the angular momentum vector of the pulley? There's no slipping between the rope and the pulley. So, first of all, to solve this question, let's read our options. So A, into the page, B, out of the page, C, parallel to the force vector, D, to the left, or E, the angular momentum is 0. So to solve this, first of all, we need to figure out our direction of rotation, right? And direction of motion stuff, right? So if we look at this is 3m and this is m. So that means that the force acting on this is going to be mg, and the force acting on this is going to be 3mg, right? So that means that our force is going to be going like so, and our motion will be going like so, right? Down, 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 like this. We're going to be going in this clockwise turning direction. So to actually solve this, you need to use the right hand rule. And, right? So to do that, if we imagine that this is our screen, right? And we know that based on the screen, this is rotating downwards. So down is our rotation. If you take your right hand, right, and you point you take your four fingers that are not your thumb, and you curl them in the direction of the rotation, right? So in this case, you'd have your fingers curled downwards like this. Imagine these arrows are your four fingers, right? From your right hand, that means your thumb is going to be pointing into the screen, right? So you can do that yourself. Curl your fingers in the direction that these arrows follow, right? And then see where your thumb points into the screen. This is with your right hand specifically, right? And this is how you solve for your angular momentum vector, right? So that means your answer is B, or not B, A, into the page. As since 2 is heavier than 1, it goes clockwise, and using the right hand rule, the angular momentum is into the page, which is A. So the correct answer is A, into the page. I don't know what the equal down into the ground. We can ignore that, right? Anyways, that's for question one. So question two, several round objects with equal radii are simultaneously released from rest and slip without and roll without slipping down the same slope. Which one will reach the bottom of the slope first? Right? So the one to reach the bottom of the slope first would be the one with the smallest angular momentum per mass, right? And that means that the largest fraction of its energy will be kinetic energy for its linear motion. So if you consider all of these and you get the kinetic energy of all of them, you'd have to use your inertia formulas, because it would be half omega squared plus half mv squared, equal radii, so the r for all of them is the same, right? You'd find the one that has the most translational kinetic energy, right, with those formulas. And in this case, that would be the solid sphere. So the answer is D for this multiple choice question. And then for 3, we need to use this diagram. So I'll just bring this down here, right? So M2 moves upwards, right? Each pulley rotates about a fixed axis through its center of mass. No slipping between the ropes and pulleys. Which of the following best describes the direction of the angular momentum vector? So if we look at this, this is going this way, and this one rotates this way. They both rotate counterclockwise, right? So again, do your right hand rule, curl your fingers in the direction of the rotation and see where your thumb's pointing. Your thumb should be pointing at you if you've done it right. And that gives you option D out of the page, right? So that is how you would do those multiple choice questions. Now this one written I have, I could have just left it at the multiple choice, but I feel like doing a written is also very helpful. So anyways, at a given instant, the 5 kilogram slender bar has the motion shown in the figure. Determine its angular momentum about G and about the IC at this instant. So the IC is not in this diagram, so we don't need to do that. Anyways, yeah. So the IC is not in this diagram. So I guess there was another diagram. So we're only worried about the angular momentum about point G. So that's great. Anyways, so we know we have a velocity at A, 2 meters per second. We have the length of the rod, 4 meters, and an angle 30 degrees. So to get our angular velocity, right, we're going to be doing the formula, which is just V over R. And in this case, R is this 4 meters, and considering this angle, so it's going to be equal to 2 over 4 cosine theta. Theta is 30, right? So 2 over 4 is a half, and then cosine 30 is root 3 over 2. So it's a root 3 over 4, which gives you, or it's not root 3 over 4, sorry. It's root 3 over 3, not root 3 over 4. Yeah. Which gives you a angular velocity of 0.577 radians per second, right? And this is, and as we know about angular velocity, is that it's the whole area. So you can take your angular velocity here at G, you can take it at A, you can take it at G over 2, whatever, right? You can take it anywhere. And we want the angular velocity around G, so we can get the velocity of G, right? We don't actually need the, yeah, you can get the velocity of G, but it doesn't do anything for the angular momentum, right? So we're just going to stick with omega, right? And angular momentum, H, is equal to I omega, right? So the, and this is about G, and we're taking clockwise as our positive. So I will put that here to the side, clockwise as positive, right? So we're going to get our IG, since this is a slender bar, right? If we look at our moment of inertia formulas, and we look here, slender rod is this one, 1 over 12 ml squared, right? So we got 1 over 12, m, which is 5, L, which is at G is 2, or no, it isn't. L is L is 4, sorry. So 4 squared. And then we're going to be multiplying by our angular velocity. And I forgot I did that. Our angular velocity 0.577. And so this is our, and I can actually write this out. So it's 1 over 12 ml squared, which is equal to 1 over 12 times 5, which is the mass, times 4 squared times 0.577, which will then be equal to, 5 times 16 times this, all divided by 12, gives us a angular momentum of 3.85 kilograms meters squared per second, right? And since it's positive, that means that the angular momentum is clockwise, which we took to be our positive direction. Anyways, those are all the problems for this chapter. Sorry there wasn't as many. If people need more examples, I can get more, I guess. But that's only if people really want them. So, yeah. Anyways, that's all for dynamics. The course is entirely done now. I don't know if anyone has other engineering courses they want me to cover. Don't ask about chemistry. I won't ever do chemistry. I could do like diff-EQ eventually, differential equations, because I like differential equations. But I feel like there's already a lot of math YouTube channels out there, right? I mean, I guess there's also probably a bunch of dynamics ones too. But anyways, yeah, that's all the learning there is to be done here. I've taught everything I know to you guys now, so you can go get good grades in dynamics. Dynamics is probably curved, so just do good against the curve, right? Be above average, and you'll get an above average grade. Anyways, thank you for watching. Hope you learned something. Bye.